Welcome back. This is Mrs. Rubright with Algebra 1 Honors. Today's lesson is 1.9, Applications of Proportions with dimensional analysis. All right, so writing valid proportions. Similar figures are figures that have the same shape but not necessarily the same size. Corresponding sides of two similar figures are in the same relative position in the figures, and the two figures are similar if and only if the lengths of their corresponding sides are proportional. So similar figures are proportional. Their corresponding sides must be proportional. So if I knew that triangle ABC is similar to triangle DEF, I could write that as triangle ABC. This little squiggly line is similar to triangle DEF. And they are written in corresponding positions. And what I mean by that is that angle A is congruent, right? Because if they are similar shapes have congruent angles and proportional sides. So angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. Segment AB, first, second, is congruent to segment DE. Segment BC, second, third, is congruent to second, third, segment EF. First, third, segment AC is congruent to segment DF. So I know all of their similarity corresponding sides and congruent angles just by looking at my similarity statement. So it's super important that you write them in corresponding positions when you write the statement. All right. So we just basically said all of this. Also, in a valid proportion, the units must be the same for all entries. So if this is all in centimeters, these need to all be in centimeters. If they're not in the same units, you need to convert them to the same units before you compare them. What change was made to make 3 centimeters is to 8 meters equals 9 centimeters is to how many meters, right? If 3 centimeters is to 8 meters, then 9 centimeters is to what? All right, so it says what change was made to make this into a valid proportion. So I guess there's something above. Let's look. So they had 3 centimeters to meters, centimeters to what? So we need to have them in what? The same what, guys? The same units. They must be in the same units. So in this case, if this is centimeters, we're going to change this into centimeters. 8 meters is how many centimeters? I don't know if you guys remember this from middle school, if they taught this to you, but King Henry died Monday drinking chocolate milk. Meters, liters, and grams all go in the middle. That's your base, right? King Henry died base drinking chocolate milk. King Henry died base drinking chocolate milk, right? So if we're going from meters, we have 8 meters, and we want to get into centimeters. We're starting at meters, and we're going 1, 2 places to the right. So that 8 goes 1, 2 places to the right. It becomes 800 centimeters. The decimal moved 2 places to the right, and we had to add zeros into those places, okay? So why and how was this change made? The 8 meters was converted into 800 centimeters. This change was made so that all units in the proportion are the same. Two figures are similar. One is measured in inches and the other is measured in feet. How could you write a valid proportion for these figures? Two figures are similar. One is measured in inches, the other is measured in feet. What could you do to write a valid proportion? You could turn the one in feet into inches, right? Convert the one in feet into inches by multiplying all sides by 12, right? So if it's in feet, say it's in X feet. If we want to convert it to inches, we multiply by feet over inches. There's 12 inches in 1 foot. Feet are diagonal, so they cancel out. So to convert into inches, we simply multiply by 12. Multiply all the sides by 12. Is it possible to write the proportion 6 meters is to x as 2 meters is to 4 meters in another way? If so, rewrite the proportion and explain how you know that the new proportion is still valid. So originally, what is it saying? Can you write it in another way? Yeah, I mean, you could write it like this. X over 6 meters equals 4 meters over 2 meters, right? It could have been x over 6 equals 4 over 2, and that would be the same thing because they're still diagonally across, the same cross products would still apply. 6 is to x as 2 is to 4, or 6 is to x as 2 is, you know what I'm saying? X is to 6 as 4 is to 2, 6 is to x as 2 is to 4. We're still proportional. These two are on the same side as these two, you know what I'm saying? So like, if I cross multiply, this would be 2x equals 24. This one cross multiplying is 2x equals 24. You're going to just get the same answer either way. They both share the same cross products. So when you cross multiply, x equals 12 for both. Solving real-world proportions. A flagpole casts a shadow that is 12 feet long. At the same time, a 6-foot-tall man casts a shadow that is 2 feet long. Write and solve a proportion to find the height of the flagpole. The man and the flagpole are both perpendicular to the ground, so they form right angles with the ground. The sun shines at the same angle for both, so similar triangles are formed. All right, so writing a proportion. His height, the man's height, is to the flagpole's height as the man's shadow is to the flagpole's shadow. Right? 6 is to x as 2 is to 12. You could also have wrote 6 is to 2 as x is to 12, or 2 is to 12 as 6 is to x, right? As long as you're staying consistent in your pattern, you're fine. So using cross products. So we're going to cross multiply and solve. So we're going to have x times 2, or 2x, equals 6 times 12, right? Divide by 2 on both sides, and we get x equals, I'm going to reduce, right? 2 goes into 2 once, 2 goes into 6 3 times. 3 times 12 is 36. X is 36. So the pole's height is 36 feet tall. Write and solve a different proportion to find the height of the flagpole. So once again, we could have set up a different proportion. So we could have set up like the flag's height is to the flag's shadow as the man's height is to the man's shadow. X is to 12 as 6 is to 2. Cross products and solve. So we would have 2x equals 6 times 12, 60, 72. Divide by 2. 36 equals x, and we get the same answer. Okay, as long as you're staying proportional, you're fine. It doesn't. The exact setup doesn't matter. Yes. Yes. Explain why your new proportion and solution are valid. Because I stayed proportional. Because I held true with my pattern. So because I stayed proportional and kept my pattern and kept the pattern. Okay? Using dimensional analysis. A can of tuna has a similar shape to a large holding tank. The can of tuna has a diameter of 3 inches and the height of 2 inches. The holding tank has a diameter of 6 yards. What is the height of the holding tank? So we have inches versus yards. We need to have the same units. So we need to change 6 yards into inches. We need to get out of yards into feet. Out of feet into what? Feet to inches, which is what we want, right? 1 yard is how many feet? 3 feet. And there's how many inches in a foot? 12 inches in a foot. So this tells me that to get from yards to inches, I have to multiply by 3 and then multiply by 12. So 6 times 3 is 18, and 18 times 12 is 216. Okay? So 216. Oh, they wanted me to write that all out. 6 times 3 times 12 is 216 inches. Write and solve the proportion. 2 inches is to 3 inches. The height is to the diameter, as the height is to the diameter. Cross products and solve. 3x equals 2 times 216. Divide by 3. X equals 144 inches. Use dimensional analysis to write the height in feet and in yards. So 144 inches, they want in feet, out of inches into feet. You have to be diagonal to cancel out. 1 foot is 12 inches. So in feet, you take 144 divided by 12, which is 12 feet. And then they also want it in yards. Well, 12 feet, out of feet, and into yards. 1 yard is 3 feet. The feet are diagonal, so they cancel out. 12 divided by 3 is 4. 4 yards. What other proportions could be used to find the height of the holding tank? Explain why these proportions could be used. So you could do, what did they do? They did the height is to the diameter as the height is to the diameter. So you could also do the height of one is to the height of the other, as the diameter of one is to the diameter of the other, right? So tuna's height is to the water holder's height, as the tuna's diameter is to the water tank's diameter. As long as you're staying consistent in your proportion, it will work. Let's do a couple practice problems. Solve each problem using a proportion. So it says that these two triangles are similar. What is the length of DF? Okay, well, we know for sure AC is to DF. So AC is to DF. AB, for a second, is to DE. So these definitely go together. All right, so we can say 3.5 is to X, as 4 is to 6. This is to this, as that is to that. Cross products and solve. 4x equals 6 times 3.5. Divide by 4 on both sides. X equals 6 times 3.5 divided by 4, 5.25 centimeters. Try number 2. Pause the video, or actually I'll give you guys some time on the video, and try number 2. You guys should have gotten that the height of the building is 200 feet tall. It is 200 feet tall. And our last example. Rectangle ABCD is similar to rectangle WXYZ. ABCD has a length of 8 inches and a height of 5 inches. Rectangle has a height of 3 feet and a length in how many inches? Well, this 3 feet needs to be in inches. So let's convert that. 3 feet, we need to get out of feet and into inches. There's 12 inches in 1 foot. 3 times 12 is 36. So we're going to call this 36 inches. Now that we're dealing with the same units on both, we can set up our proportion. 5 is to 36 as 8 is to what? 5x equals 8 times 36. Divide by 5. Take out my calculator. 8 times 36 equals, divide by 5 equals, and I got that x is 57.6 inches. All right, guys. Your homework on this is page 57 and 58, and in addition to that, you also have page 65. I hope you guys enjoyed the lesson. Please like and subscribe and have a fantastic day.